And honored that the topic of artificial adaptive intelligence is driving attention here in Hong Kong. And also I know that we have participants from overseas as well. And today I will share my thoughts on the current state of the industry, on the direction that we work with my colleagues, and I will explain why we believe that artificial adaptive intelligence is the missing stage of machine intelligence between artificial narrow intelligence and artificial general intelligence. And it will be definitely longer than 1 hour talk, so please be prepared. Organizers told me that we don't have any time limitation, and you see I have even a cup of tea with me, which is rarely the case. I'm usually quite light, but when you give several presentations in a row that are quite long, you need to think about the health of your voice, and I hope that I will manage to be as concise and detailed as I planned to be from the beginning. So let's jump straight to the presentation itself. And I need to start always with the slide that I hate the most, because I need to tell you who I am and try not to make it look like I'm bragging. But most of you already are familiar with my work, obviously. I'm Boris, and I do research on the topic of dynamic intelligence, and currently I serve as a reviewer at Springer, at IEEE, MDPI, SPIE as well. I'm with the Hong Kong University of Science and Technology, and also I'm CTO at Strevio Limited. We need to start with a quote, and this quote is the whole lecture's guiding sentence. I want everyone to look clearly at the screen and read it with me. A system is adaptive, not because it learns more, but because it requires less to be told. And the whole lecture will be built around this quote. This is what we will try to prove, both empirically and mathematically today, but still try to be as simple as possible, but not simpler as Albert Einstein was told. The 3 points that I need to highlight that can be derived from this quote. Adaptivity means needing less instruction. Not bigger models, but freer ones are the future of artificial intelligence. And we will also discuss why the current idea of scaling models and trying to improve the generalization of the models by just scaling them is not the right way to go towards AGI. And everything that we'll discuss today will follow from this quote, as I said. We are currently somewhere in between, and everyone understands that. We have a very clear definition for artificial narrow intelligence, but at the same time, all the definitions that you hear for artificial general intelligence, the single model that is as powerful as it should be to work across domains, to reason independently, to learn and itself like a true intelligence would, is quite hard to define clearly. And without clear definition, we cannot really move forward, because how you can try to achieve something that is not mathematically defined. There is a left pole, narrow systems. Anything from stimulus response agents for chess, speech, vision intelligence, and we have extremely clear understanding of that left side. And there is a right side, this imagined general intelligence that we understand is probably reasonable to move towards, but there is a huge blank space in between them. And we are currently in that blank space. And with this presentation, we will try to fill this blank. We will try to explain why we think certain actions are needed right now and what is the vector of the general direction for the development of AI. We will start with adaptivity. This is an important topic to understand, and we will clearly define it in math as well. The definition that I propose in my book is quite sharp. A system is artificially adaptive on a family of tasks. I want to highlight it, on a family of tasks, because adaptivity can be defined only on a family of tasks. That is a closed solution space. If it performs competitively with a specialist baseline, needs no human set knobs that depend on a specific task, and reconfigures itself from what it infers about the task itself. First of all, it should be competitive. It should work at least as well as narrow systems would perform on exactly the same task. Secondly, no task-specific knobs. It means that we don't need humans be involved to retune the model on that task. And this is also quite understandable. And the last point, the third one, self-reconfiguring. It means that the system should understand itself, its structure, the input and output to adjust the architecture on the go. And we will also discuss later what are the common ways it can be achieved even nowadays. This is a very precise definition for adaptivity and the system that is artificially adapted. And also throughout this lecture we will come back to this definition many times, so please take a look at it right now and try to understand the 3 points that we define. It is competitive, no task-specific knobs, you don't need humans to tune it, and it is self-reconfiguring by understanding its structure. Okay, so we're moving on to the next slide. Why these 3 clauses are needed? If you drop the first one, a system that does nothing needs no knobs. So basically it prevents uselessness of the model that we develop, because if it does not perform at least equally well as other narrow systems on that task, then what even is the purpose of developing that model? And we should stay quite pragmatic. Again, if the model is not competitive, why we should even develop the model that way, right? So if you drop the second clause, no knobs, but secretly retuned each task independently, we block hidden tuning, because nowadays, even if we know that there is certain architecture that works quite well, for instance, we take the domain of computer vision and we take the convolutional neural network, can be any architecture, let's take ResNet. There are still so many parameters that we need to tune, and even though there are many sets that we know will work quite well and are quite generalizable, we don't have a clear mathematic definition of why this set of nodes should be taken. In most of the cases, we just take something that, based on our experience, we understand will work quite well, and that's it, we'll stop here. But this is not the case. We should try to step out of our perception and think about the future. And of course, this is the exact definition of hidden tuning that we don't even think of as tuning in most of the cases, but it is in fact a human work. And if you drop the clause number 3, preset once and frozen. This is how modern deep learning is working in production. You develop the model, you freeze it, as it is, you deploy it, then data shift happens in a year, in half a year sometimes, and that's why you constantly need to retrain the model on the recent data. You need to improve it and redeploy again. But once we achieve adaptivity, this is not the case. The model should understand the distribution change, should understand the input data, and change its structure accordingly. This is the major factor that defines adaptivity. This is the time for the tea, I tell you. This is the definition that is falsifiable and countable on purpose. We can count the knobs a system exposes. We can count how many parameters need to be tuned by a human. And actually, we never say that we should achieve the state where no human tuned parameters are present. What we say is that we should try to minimize them. And also, we can test whether it stays competitive. We always know the benchmark. We always understand what are the state-of-the-art approaches for a particular set of tasks. And that's why we can measure whether on our specific task the model performs at least competitive. So a claim of adaptive can be proven wrong. It is not a slogan, it is a measuring stick. It is something that is clear, unlike the definition of AGI. And to measure adaptivity, we define the Adaptivity Index accordingly. You can look at the formula right here, and you can see that we measure the Adaptivity Index for a system S on a set of tasks tau. Here H is the expected number of human set tunable hyperparameters to deploy the system S. H max is the same count for a fully hand-tuned specialist baseline. For a fully hand-tuned model, narrow model that is not adaptive. Rho is the performance ratio of system S to that baseline averaged over T, and the score of 0 means that the system is fully narrow, and 1 means that the system is fully adaptive. It's extremely hard to achieve the adaptivity level of 1, and we will show examples later, but at least this is the scale that is very clearly defined. It is easy to understand, and most importantly, it is scaled from 0 to 1. As I stated in the previous slide, reading the two endpoints is very easy. The adaptivity of 0 means that the system is fully narrow. It means that either H is equal to H max, meaning no tuning is absorbed, or rho is equal to 0. It means that the system doesn't work, means it's not competitive on the baseline. And adaptivity index of 1 means that the system is fully adaptive. It means that either H is equal to 0, there are no human tuned parameters, and at the same time rho is 1. It means it matches the specialist baseline performance level. And the product structure is deliberate. You cannot buy a high score with one term alone. Either you have a system with no human tuned parameters that performs poorly. We see it in modern life all the time. It will still achieve the score of 0 because it is not adaptive, even though it is competitive. Okay, so with this in mind, if you drop the bracket, you will reward systems that perform well but need many human tuned parameters. And this is why we try to eliminate this hidden tuning. And if you drop raw, you will reward systems that actually do nothing but need no parameters to be tuned by humans. And as I stated before, we should stay pragmatic. If the system is not matching the baseline of standard performance, we should not care whether it's tuned, untuned, how much time a human needs to put into the system to achieve the competitive performance. Okay? Useless systems are not what we are interested in here. And a multiplied score, it forces a system to be simultaneously no-blind, meaning as less human-tuned parameters needed as possible, and competitive at the same time, which is exactly the artificial adaptive intelligence claim. What you actually need to compute when you deploy the system is here. Let big H for a system S be its hyperparameter set. For each hyperparameter in that set, we have the adaptivity index measured. And it will be how much S sets itself as a measure. This is the formula. It is in front of your eyes, and look at the points below. If the adaptivity for a hyperparameter is 0, it means that a human or a human chosen default sets the parameter, and it contributes with the weight of 0 overall to the total sum, as you can see in the formula. If it's equal to 1, it means that S sets it by task conditioned inference, and no human judgment is needed here. The weight is defining the operational significance, which is normalized. And this is what you need to measure at the deployment stage, the operational form of the overall system adaptivity, the big alpha, okay? I need to mention 3 things adaptivity is not. It is not flexibility, because flexibility is the range of behaviors. Many people confuse adaptivity with generalization, but generality is the breadth of domains. We can work within one domain, but still be adaptive. Online learning is getting traction, and adaptivity can be actually something close to online learning, but unless it's self-driven. So again, we should come back to the definition. It should be self-reconfiguration that we see within the system architecture. The conclusion, small conclusion for this slide is that adaptivity is autonomy within a range, not the range itself. You see how it is starting to be shaped as something quite different from AGI, but still measurable, because we define the range. Within that range, on a specific set of tasks, the system can be adaptive. AGI is something without a clearly defined range. That's just the very first idea I bring you after we have went through just the introductory slides, okay? And it already starts to be shaped clearly, and that's actually the goal of this lecture. Remember, always remember, adaptivity is always for something. A system is adaptive for a family of tasks. I have just started my talk mentioning that. You can be brilliant on one family of tasks, but quite useless on another. And we should accept that. We should admit that. The progress means widening the families it covers And that widening itself, in our opinion, is the road towards AGI. Now we move on to the next part. And in this part, I will try to explain my personal understanding of why scale is not enough for us to move towards AGI. The popular belief is that bigger models can do amazing things. And there is some kind of industry that just keep scaling, keep adding more data, and you will improve. You will improve on the benchmarks, you will improve generalization of the model, you will improve even the protectiveness of the model against adversarial attacks and so. But the gap to AGI is not quantitative unlike it's seen. And it will not close on its own. The pushback, I have already started that, but I will mention several points. You see the chinchilla law to the right of you, and the new capabilities are genuinely real. The capabilities from scaling the models, language models, to large language models, building on top of that, reasoning and so on, but the conclusion doesn't follow from what we have right now. Scale makes narrow AI broader, and it may confuse people that we are really improving, but it does not make the model general. There are 3 tests that I believe are a true bridge to AGI. The first one is coverage. It can handle many tasks, and it can handle many tasks naturally, not just by adding more and more processing channels, like you have the text embedding, then you add vision embedding, and you say that okay, now we can do both text and images, and then later we can even do videos, but that's not how it works. Autonomy, that's what we're clearly missing. Adapt with no human. You cannot just train a large language model, then deploy it as a chatbot interface and think that this is a true general intelligence that is compressed into a kind of matrix stored somewhere in a server. It's a very wrong and dangerous perception. Structure. Change its own shape dependent on a specific task required. There is also something that modern scaled models alone cannot achieve. And as I just mentioned, and you already inferred my opinion, the scale that we have right now, it barely passes only the first one, coverage, and in a very robotic, in a very mechanic way, not in a way that flexible, adaptive, intelligent systems in real life will do. On coverage, foundation models do almost everything. At least there is no theoretical way to prove that wrong. You can generate poetry, you can discover laws of physics, chemistry, biology, you can deploy them into a legal system, you can generate code, you can do translation. And all of these tasks can be achieved through a single model at the level near a competent human generalist professional will do. And on coverage, a scale that we have right now is a triumph. But autonomy, that's where scale starts to sample. Choosing the prompt is already a hyperparameter. Choosing the fine-tune rate is a knob. Choosing what to retrieve from the document and ask your large language model to do it is a hyperparameter itself. When you try to improve the performance of the model by augmenting its input and try to feed more generalizable variety of data, same you can do with output, it's already a human judgment involved. It is a knob. And we do it to prevent overfitting. But who told us that the way we look at the model architecture is the correct one? Scale fails at the structural level. This is a classical convolutional neural network for image classification. In this particular case, we have the digit classification task. Why we choose this number of convolutions? Why we choose this number of pooling layers? Why we choose the size of input for the image? Why we do not degrade that? Well, there are empirical rules that help us to find near optimal results, especially if you are for many years present in the industry. But at the same time, making a step back and thinking, I understand, generation of any type of artificial narrow intelligent models is as fixed in shape as the systems they replaced. You want to improve your model after half a year of deployment. What you will do, you will take the architecture, you will build a deeper model, or you will improve the hyperparameter set, or you will improve the quality of the images. But more importantly, the set of hyperparameters that was present in the model 1 will be exactly same as in the model 2. Even though model 2 will be stronger on the benchmark, the number of hyperparameters will be same because the architecture is fixed. So in my humble opinion, we can compare the current state of the industry with a peer. There is not a bridge that we are trying to build towards AGI. The coverage that we have right now, it extends the reach, but nothing more. Reaching does not mean arriving. But what I want to highlight is the path to AGI is not by scaling. And by concluding the slide, we're concluding this section and moving on to the next one, where we will define the hidden cost and elaborate more about the hidden cost of deployment of AI systems. This is the task that nobody actually reports. Real cost is not about compute, it is also not about the data. It correlates with both of them, but in fact has nothing to do with only them standalone. It's the cost of humans tuning the burden of the system, and it is hidden behind clean benchmark scores that people don't even think about in most of the cases. It grows as tasks drift from defaults, and that's why we need to do the auditing of the system, redeployment of the system to maintain the cost of maintaining the system in a reasonable range. But that's the tax that we pay after the deployment of any intelligent systems. There are many decisions that we should think of when deploying a system, whether it's about architecture, the depth of the model, the width, attention pattern. It can be anything. For optimizers as well, learning rate, schedule, batch size. There are also other ones that are not less important, such as loss, regularization level, augmentation, early stopping. This is all parameters, all factors that a deep learning engineer needs to think of. And often, more than 50 human decisions per project are present. That's why we define something very important: the principle of conservation of tuning. Exact as a conservation of energy, here we have the conservation of tuning. Everything in this lecture that is highlighted with red color should be red as it is. So let's do it together. Every configuration decision is made by someone or something. A decision not made by a human is made by a default or by a search. It is never simply absent. What it means, let's think together. There is no hyperparameter that ever truly disappears. It only changes who pays for it. Autonomous often means paid elsewhere, and our job is account for every payer in the system if we really want to minimize the parameters that are tuned by human to achieve adaptivity. I call this slide the invisible repair crew, and let's think why. When the model drifts, alert fires, and engineer retunes, that's how the enterprise level grade stack for deep learning works. And this never appears in the paper. It's not something that we discuss outside of the small room of engineers. From outside, it looks quite autonomous, but from the inside, it's quietly rebuilt by hand every time something breaks. And this is us, engineers, the invisible repair crew behind any deep learning system deployed. And the true cost of narrow AI, even though it does not sound fun, but yet is important, is defined here. Not the one-time training bill. It's not something that you need to spend once to train the model. The endless upkeep bill, indeed, the machine alone wouldn't survive, even after it is deployed. There are many reasons for that. It's not about today's lecture. I'm sure that everyone in this room is competent enough to understand why. It's really a human-machine cooperation. It's what we pay for, human-machine cooperation. And in this particular case, human part is more costly than a machine part, oftentimes. Part 3, we are moving towards the definition of the thesis statement, and probably, arguably, the most important part of today's conversation that we have. The thesis in one line, again red, we read together everything that is in red, we read together. The missing piece between narrow and general AI is not scale. We have argued that already, and is not generality. We briefly discussed why. It is adaptivity. The power to reconfigure itself without a human stepping back in. Scale gave us breadth, and we can use that to solve many tasks that could not have been solved at the human achievable level before. But adaptivity is what gives us autonomy by definition of this book and conversation. This is the neglected middle stage, and we try to defend this claim today, that adaptivity is something that will bring us closer to AGI. I find it actually quite important today to redraw narrow. We think that narrow is something that is stuck in one domain. You have the convolutional neural network trained for image classification, and this is one domain with very limited functionality, and we can only work with this architecture, with this model trained within this domain. But the idea should be redefined actually. Narrow is something that requires human adaptivity, human judgment involved when things change. And we know that environment around us constantly change. That's why we need to change our approaches as well. Human from the outside, it is narrow. But what we should be looking at is system from within. This is adaptive. An adaptive system, a system that does not require human to step in all the time. The surprising consequence of that redefinition for narrow AI is that foundation models are mostly narrow, because every time you want to improve something, you need to retrain the foundation model. Reprompting is human adaptation. Calling it prompting, prompt engineering, changes nothing. Capability and narrowness are two separate axes, and we should not mix them. But we should be also fair about narrow AI. It is highly predictable on familiar inputs, and in real life, when scaled, predictability of the system behavior is key to long-term success. It is easy to test, easy to audit, and easy to certify. It is cheap for stable, narrow tasks deployed long-term. Don't abandon it, and we should not. But we need to accept that we outgrow it, and it's a high time to move towards something bigger. Well, you know that I do research, but I still come from an industry background, and that's why I can tell you why systems break in production. There are 4 ways, more important ones. Covariant shift. This is what I called data drift, but we define it more clearly now. When inputs start looking new to the system, that happens oftentimes in the industries where the user behavior is judged, because user behavior changes over time. If you work in retail, yesterday you have one category that is popular, tomorrow you have another one. Label shift, the mix of answer changes. Again, data shift, data drift is related to both of them. Concept drift, this is actually the most dangerous one, when rules themselves change, because you need to rethink the whole architecture of the system. The adversarial shift, when there is an adversarial attack on the system, when someone attacks the system on purpose. And today, all of these breaks need human to be fixed. And this is where the cost for maintenance comes from. What about AGI? We have defined artificial narrow intelligence. We have defined artificial adaptive intelligence, and we have argued why we should move from one to another, but let's also say a few words about AGI. We have just started the first slide of this lecture, that AGI is a mess of definitions. But there is something that is clear. First of all, the breadth. We have mentioned this word several times already. It means that the system can do any human task, okay? Very vague in mathematical precision, but quite understandable conceptually. Transfer can learn any human task when has enough sufficient training examples to be learned from. Ensemble, it is an important concept for machine learning. A checklist of abilities. You combine several independent abilities to not just be stronger on a new one, but also to be stronger on each of them independently still. And mechanism. Well, one magic underlying process. We should somehow combine this all together into one definition. And I have asked this rhetorical question already, and I will repeat. How we can build something we cannot clearly define? With no mathematical definition on paper, nothing moves in the world of AI, believe me. The quiet realization for me was that there are a list of problems that we understand need to be solved to reach AGI. Out of distribution, forgetting, self-monitoring, definition of goals. But when you look closer, you understand that all of them are actually adaptivity problems. AGI research itself in the core is adaptivity in disguise. But yet, even though we don't have mathematical definition, we are running towards AGI. And let's make a pause and think why aiming straight at AGI fails. The open problems are adaptivity problems. We don't have time to elaborate why, but let's fix it as something we understand. Adaptivity, unlike AGI, has concrete near-term targets and mathematical definition. Going straight for AGI skips its own foundation. Adaptivity is the road, not a detour. It is the road of discovery, the road that we need to pursue to get closer to AGI. Will it be a next step, a foundation? I don't have the answer right now. But what I understand is that this is the future of the next 5 years of research for AI community. So how we can test whether the system is adaptive? First of all, it configures itself from the task. It means that it understands the task and itself to configure based on these two independent inputs. It notices the environment changes, regime changes, unprompted. Exposes only the unavoidable knobs. It means that we should always minimize the number of hyperparameters present in the system and try to minimize them for a human to be tuned by. But we should never eliminate them if it's impossible to achieve competitive performance. And it adapts without forgetting. I think that catastrophic forgetting is a real issue nowadays with foundation models. And more importantly, again, this is not the topic of this talk, but mathematically, catastrophic forgetting cannot be eliminated from the current structure of the foundation models. You can try to minimize it, you can try to work around that, but you cannot remove it. And we as humans, we don't just randomly forget something that was quite important, right? Unless we are stimulated to do so, right? So this is another distinction between modern AI and how we as truly intelligent organisms reasoning in the solution space. A few words said about AGI. Now let's discuss parametric minimality. And I have personally put a lot of effort in deriving the principle of parametric minimality in a formula that I think compromises all of the sides responsible for a deployment process of the model. Alright, we have the adaptivity profile of the system. It contains parametric minimality, transferability, regime awareness, self-reconfiguration, and performance retained from a benchmark. Basically, everything that we have discussed so far is the adaptivity profile of the system, P from S, okay? Quite straightforward. I just wait for 3 more seconds for you to capture that, and I move on to the next slide. The full census is achieved when we understand 3 things. Defaults are decisions by other humans. No other parameter that is left untouchable should be considered as something that is optimized without human judgment. It means that someone else put a lot of reasoning to define the parameter that you are comfortable with. 50 knobs, 48 default are still 50, even though you don't touch 48 for a reason, for a rule that you came up with. The hidden choices remain still real choices, choices that probably someone else before you made, or someone else designed a way to find the solution that you are currently satisfied with. And we should count everything, including the inherited defaults for the system. It brings us to a minimal tuning objective. This is the minimum total surface area cost of all the knobs that we take into account to achieve the required performance floor for the system to produce strong results. And we minimize the exposure, yet understand that it is the subject to competence. Formula looks scary, but just think of the words that I have mentioned right now. I hope that I'm not moving too fast actually, but again, we take 10 more seconds to process it together. The minimal tuning objective that we define mathematically is the total surface area cost of knobs that we try to minimize, take into account that we reach the required performance floor. Okay, moving on. The conservation of tuning effort derives 3 points, and you see I try to structure it actually very clearly. We have slides, minimum text. I don't throw random math into you today, and also I try to structure it with bullet points. So the conservation of tuning effort, not human decided, means default decided. Okay, we have mentioned it already last 2 slides. Not default decided means search decided. There is a search, it can be an algorithm, it can be a set of algorithms, but you can still find algorithmically, programmatically, systematically the near optimum set of parameters. And the cost is relocated but never removed. The same way energy never emerges on its own, never disappears. It is transferred from one state to another. The cost is relocated but never removed. This is the way I personally define the conservation of tuning effort at the deployment stage. A conservation law for configuration burden. So let's repeat it. Not human decided means default decided. Not default decided means search decided. Cost is relocated but never removed. This is actually the key sentence. So moving on from the conservation of tuning effort to the discussion of high surface area that isn't inevitable. We have compilers and they have absorbed their configuration over time. We all understand how compilers work because we have the fundamental computer science education. Databases and schedulers actually did the same. And machine learning simply hasn't matured yet. Maturation, looking back at the history of computer science and engineering, not the architecture itself, is something that removes human judged knobs. It means that the industry is absorbing the experience, absorbing the understanding of the playground, and helps us to derive rules that removes human judgment into a set of optimal parameters needed for each independent set of tasks. That's why we should connect it to MDL, This is actually the slide that may sound confusing because the three letters MDL never appeared, but you see that the parameters are called MDL, and that's why I call it the MDL connection. Look at the formula closely. The big L is the cost to describe the model, and the cost of the model description is directly related to the cost of data given the model. If you have exactly the same data set, but you use a shallow model and a deep model, you understand the difference in the cost to describe the model. To describe the model means to train the model, to deploy the model, to maintain the model. That's why the big M with a star here is equal to the minimum big L, the cost of the model description, and the cost of data given the model description. And that's what we try to minimize. The cost to describe the model is related to a human effort, and the cost of data given the model is derived from that. So this is something conceptual. Now let's make it more clear. Optimal complexity is set by data. You will never choose a super deep model for a tabular data with 1000 independent rows, because you understand that the complexity of the model is set by data. The maintenance cost is set by the model complexity. Now, when I translate this mathematical formulation into these two sentences, everything actually starts to piece well, right? We all know the cost of maintenance and the development in AI world. And now we understand that actually when we want to minimize that cost, this is the combination of the optimal complexity that is set by data, the model complexity, and the maintenance cost that is set itself by the model complexity, right? So, and now everything makes sense. Immediately makes sense, but this is directly reflected in this formula. Why we need it? Because we will discuss the data determined optimum, and the next slide will be the 3 pathways we can go to improve the adaptivity of the system. But coming back to the data determined optimum, it's something that I think we just need to spend 1 minute on. Overconfigured systems burden users needlessly. Okay, we always want to achieve the minimum number of configurations needed to achieve the performance level that we're actually satisfied with. And unlike the overconfigured systems, underconfigured ones sacrifice the real performance because they lose generalization, and the data fixes the right target. Okay, we don't want to have the underconfigured systems because we don't want to sacrifice the performance. We want to perform well on a large set of tasks, but at the same time we don't want to go too narrow. We don't want to overconfigure the system. And the data complexity fixes what is the system choice. This is another translation of the slide before, but that slide we try to quantify the cost, and here I just elaborate how really the choice of the model is happening in the world of artificial intelligence engineers. And the small conclusion for this slide is that the data chooses the complexity of the model, the complexity of the system. I don't like the word model, that's why probably we can call it a system. So the data chooses the complexity of the system in the ideal world. And actually we all need to understand that if you want to provide your clients with the most optimal solution, not just solve the task, but solve the task efficiently, then you clearly need to understand that. Yeah. And with that all in mind, we move on to the examples and to the 3 pathways we can go to achieve adaptivity. So the three pathways we can choose are mentioned in the slide. We can choose to achieve adaptivity, higher adaptivity level for the system. The pathway 1 is configuration choice before training, and actually we will go through each of them in detail now. Pathway 1 reflects that the system needs to understand the data, and based on that data distribution, self-configure during the preparation step before the training. Pathway 2 is structural and evolutionary morphing during training, and pathway 3 is self-adaptation during training. Self-adaptation can be based on the data distribution understanding or based on the task understanding, but the system should be able to change the structure during the training process. And 3 timescales, but 1 shared goal. When all of these 3 are present, the system is highly adaptable, but we will also mention why it's quite hard to achieve all these 3 work together in combination. The configuration choice before training is probably the more straightforward to start with. It means that the system understands the data and the task before configuring and can make the decision based on that. A good example of that is ORCA, Online Regime Correlation Analyzer. It's the system developed by us, and it inspects the eigenvalue spectrum of the data. The random matrix theory, okay, we need to understand that. I hope that everyone here is either familiar with that or will just understand the overall idea as a whole. But the goal is to detect when statistics change. The goal for ORCA is to look at the market as a graph representation of industries, types of assets, different locations being connected to each other and working as a unified system, and then monitor the changes in the behavior of that system using the random matrix theory to configure itself before training and predicting whether within the next 3 days we will see the drastic market movement up or down. Basically, this is one of the strongest reactive predictive crash detectors present. It's not magic, it's the way to monitor the behavior, to alert unusual correlations present in the dense network. Another example is PSTNet, a system that inherits fundamental laws before configuring. Physics-informed AI is actually a very interesting way to go, and this is one of the major directions I'm personally working on. The idea for the systems like that is to inherit laws of physics, chemistry, biology, and to help the system discover it independently and come to a stronger conclusion. So in the case of PSTNet, it doesn't learn the turbulence exponents, and the goal of the network actually is to predict turbulence levels at different flight levels, okay? It takes them, the turbulence exponents, from established physics laws. This is the strongest form of pathway 1. The parameters are removed because a scientific law determines them. So there is no human and no search involved ever to choose them. Very interesting way, very interesting way. The structural or evolutionary morphing reflect the idea that architecture is built, it is not pre-specified. And the example of that is, for instance, MorphBoost. MorphBoost is an algorithm developed by us that grows each tree of the gradient boosting algorithm. According to residual structure, it interpolates before pure gradient-based gain and time-evolving information theoretic component as learning advances. This is the first algorithm in gradient boosting theory for classical machine learning that does not have static ways to split criteria definition. It means that the choice of where to grow the tree is happening during the training process based on the information theory that is happening inside of the training loop. It is the dynamic way to change the structure of the tree during training. This is a very powerful and yet quite understandable conceptually. That's why I like this as an example. Morph Boost is using the structure to achieve state-of-the-art performance, outperforming XGBoost, CatBoost, and we are actually very proud that we have developed that. Another good example is Elena, self-adaptation during training. The network that understands itself. This is just one example, and there are many more. So Elena, in this case, takes a very different route. It uses bio-inspired route. It takes epigenetic tags to assign the tags for each learning parameters, as you can see here, and uses an evolutionary algorithm to grow the control tracker. We have the mutation resistance, the crossover affinity and stability score assigned with each learning parameter that forms a sequence of learning parameters that form a population that is later independently developed for each of the learning sequences. And for each learning parameter, we will get a very different set of mutation resistance, crossover affinity, and stability score rates that helps to understand where to go during the training process. Another way for self-adaptation during training is the understanding that the final goal for engineers is to adapt the resources, not just the weights. We don't just tune weights when we train the model. And the example is, for instance, QKiWiCom. It sets the compression from the cache utility. There is another example, a Shepherd grid strategy that infers coordination from geometry. And I don't want to make this lecture overly complicated, but the idea is same. The budgets, they respond to demand automatically. That's what we should strive for. Efficiency in this case becomes inferred, not hand configured, and we let the algorithm define what is the budget and what is efficiency. At the same time, we still maintain the understanding of what is the range where the algorithm operates in, and it's still self-explanatory in such case. We define the range. The range is not defined by the algorithm, but what the algorithm does, it finds the right set to define the budget clearly, not just the range of the budget. How these three combine? How three pathways combine? Well, first of all, we fix the architecture to artificial adaptive intelligence first. Secondly, we set the initial values from data understanding. This is a very powerful idea that we first need to understand the data, variation, and distribution to make the first judgmental decisions about the architecture of the system. And after that, we track the performance and adapt the structure during training. This is, in my opinion, the ideal example of the artificially adaptive algorithm. But, as I mentioned already, combining these pathways can create new instabilities. What are the instabilities that we can see after the deployment? First of all, it is a closed loop and self-modification. And when we deal with closed loop systems and self-modification there, we always find that the systems may be quite hard to stabilize. Why? Because there is always drift in usage. Even though we may have not drift in the system training loop, we may have the drift after deployment and the misleading signals that threaten the overall reliability if the right of metrics is not clearly defined correctly from the day one. We log trajectories, provenance, and decisions. And in this case, auditability becomes non-negotiable for adaptive systems, because adaptivity is something that is possible to measure and helps us to reduce the human burden. But at the same time, human judgment will be needed to audit the systems, to maintain the systems, and to understand conceptually what can go wrong. And these are the risks that I need to mention. And we already see these risks. We see these risks in the systems that we deploy for existing clients, both institutional and academic and industry clients. And we understand that auditability becomes a very important role in the 21st century, especially for AI, for something that is operating independently, not a human, okay? And in the very end of our discussion, I want to mention my thoughts on what artificial adaptive intelligence that we have defined today lacks in comparison to AGI. As I said, AI absorbs configuration. It is the adaptivity within the range set, but not the range itself. It means that it absorbs configuration, but not the goals. It does not operate towards the goals that it chooses independently. The goal is chosen by a human. It is necessary for AGI. Adaptivity itself is necessary for AGI, but it's not sufficient. Adaptivity is prerequisite, but not the destination. Even though we argue that adaptivity is the next step for the whole AI world, we also accept that if we want to achieve the general intelligence, adaptivity is not enough. Okay. The closing refrain for this lecture, the last slide. Progress is hyperparameters and human judgment being removed from decision-making loop, not added. We remove from human responsibility specifically, but AAI, artificial adaptive intelligence, is the only quantifiable path that we see right now towards AGI, and we should all focus on going in the right direction. It does what compilers did for hardware. It will do its job for the whole world of artificial intelligence. And with this in mind, we will go to a Q&A session. We have 30 minutes of Q&A session as well today. And I hope that this lecture will help you in the first place. Students, I know there are many students here, professionals, engineers as well, to think differently about the systems that you deploy, about the systems you develop, about the models you build, and also about research you do. Thank you very much for being here with me. It's sincerely very important to me that we have hundreds of people in the audience. Very important. Thank you.